This video is entitled Hyperbolic Functions. Now let's take a look at what the basic idea of a hyperbolic function is. Notice they have trig type names with h at the end of it, but notice their functions are exponential functions e. And I just put a couple of graphs down here. So you see the hyperbolic sign is e to the x minus e to the negative x over 2. And hyperbolic cosine is e to the x plus e to the minus x, all divided by 2. There's the graph of those. And similar to the trig functions, they have the same kind of relationship that hyperbolic tan is hyperbolic sine over cosine, and hyperbolic secant 1 over hyperbolic cosine, so forth, so on. Here's an example I found from a book just to show you a real-life application of where hyperbolic function is used. And the St. Louis arch, which looks like a parabola, but you can see the hyperbolic cosine looks like a parabola. Now it's negative here because it's going downward. So basically 600 feet across. So if you start with x being in the middle, 300 feet one way, 300 feet the other. There's the equation. I think it would be kind of interesting to see how they came about with that equation. And so anywhere the range of values of x, you can put it in there and it'll tell you the height of the arch at any point in time. Now let's take a look at the derivatives and antiderivatives of hyperbolic functions. Now you have to be careful, so you kind of want to have access to these. They're a bit. There's two of these that are a bit different from regular trig derivatives. It's the hyperbolic cosine has a derivative of positive hyperbolic sine, where of course regular trig, the derivative of cosine is negative sine. And what's the other one's different here? This one's okay. Tan is sec squared. Cotangent h, negative cosec h squared. I kind of get tired of saying hyperbolic after a while, so I just call it h. So sec h. Now this one's different than trig. Trig would not have a negative sign here for the derivative of just secant itself. Now the derivative of cosecant h has a negative, so would regular cosecant. All right, well, these aren't too bad. It's just now we have just basic skills of taking derivatives, whether it be chain rule. Now notice this one does have a h cos here, but the primary function that we're differentiating is natural log. So the derivative, of course, of natural log is u prime over u. So it would be the derivative of h cos over h cos, which the derivative of h cos is positive h sine. Once again, right up there, positive, not negative, over h cos. And on a handwritten answer, I wouldn't care if it was left just like this. But yes, that could be then translated to h tan. Now here's h sec squared. So I'm going to treat that as your u, put the exponent here, and just kind of off to the side here to give myself a little guide of what I want to do here. So basically d dx of u squared then would be 2u du dx. Obviously you don't need to do that. If you don't need to do that, don't worry about it. So I bring the 2 down, change that to 1, which obviously I can get rid of the 1 there. And then I'm taking the derivative of the u, the derivative of the inside part, which that also has a chain rule to it essentially, because you then have to remember to take the derivative of that 3x itself, which is this 3 right here. So you see it's negative h sec 3x times h tan 3x, and then times that 3, which is the derivative of 3x. So I just put the loose terms all together just to make it look better. So 2 times negative 1 times 3 makes negative 6. And I combine the two h secs together to make h sec squared. Okay, that's just more cosmetic here. The blue part here has the derivative correct there. So, all right, let's just take a look at this. Obviously, this kind of works sort of like a trig function would. You'd look at this and go, hey, what I want my u to be to help me get that du on top. In this case, you want h sine to be the u, because you can then write that as u squared, because its derivative will give you h cos. And then now everything fits beautifully. A would be 3, nothing to adjust. So you're looking at du over the square root of 9 minus u squared. And that is inverse sine, also known as arc sine. Either way is acceptable. So the answer is actually then the arc sine of hyperbolic sine of x over 3, and of course plus c. And just kind of give you a little different flavor there. Notice I took the square off of here, which in that case you want u then to include everything since the square isn't there. Yeah, so here we couldn't because the u was only the sine and the square was, we just made it u squared, so you couldn't include the 9. But now we include everything, so the derivative will be negative h cos. So we have to adjust this for a negative. So now this is not arc anything. We're just integrating power rule of u to the negative 1/2. So, n plus 1 over n plus 1, that will give you negative 2u to the 1/2. And then you can replace u. I didn't bother to use a radical, but I just wrote it as negative 2 times 9 minus h sine x, all to the 1/2, plus c. Okay, I'm going to take a brief look at the inverse hyperbolic functions. I'm not going to worry too much about the derivatives. But actually, if you were given these inverse hyperbolic functions, you can just differentiate them as you would any logarithm. And the fact that these are all logarithms is because of the fact that since the regular hyperbolic functions all involve e, so the inverse function of e is ln. So if you were, not that you should ever have to do this, but if you were algebraically solving for the hyperbolic function inverse, you would see that it was ln. I decided to include, just real quickly to show you this hyperbolic and then versus the inverse. Now notice that the idea on the graph here is that, that's true for any inverse, that an inverse function is always the mirrored image of the graph across the line y equals x. But I don't know, I can't imagine any instructor trying to have you do this. I would hope not for exam purposes, but I'll zoom in on this. So basically, you're reversing the x and the y to solve for the inverse function, and that's essentially what happens. This I thought they'd do a little differently, but I would have done it as I would have started with the which that's the correct form for the inverse. I mean the hyperbolic sine, but then I would have put an x on the left and then y is on here. But it does work itself down into a quadratic. So I guess they just decided to do it this way and just solve for e to the x, which is fine, and then ln there at the end, and they end up with result for the inverse hyperbolic sine. So okay, but that's hopefully a mess that you won't have to expect to solve yourself. All right, so I won't worry too much about those. But now I'm going to come down here and focus on these, what I think are interesting integral forms. So we have these three that we've learned before for inverse sine, inverse tan, that would lead to inverse secant. Now these three on the right actually, because you see these functions, all these natural log functions, they're inverse hyperbolics. But when I ask these questions on tests, I just want them to be integrated and come up with these results in terms of natural log. I'm not expecting anyone to know that if it's inverse hyperbolic sine or inverse hyperbolic cosine. And it's kind of interesting if you put this in some sort of software like Maple software or whatever, and you integrate these, it'll show hyperbolic inverse as the result instead of this, but it's the same thing. So let's come down here. All right, let's see. Now, like anything, before you worry about what the answer is going to be, you want to make sure you get it up set in a proper, u du form, then you can worry about it. I mean, yes, I put the correct formula out over here to the right, but I wasn't even thinking about that when I first solved this. So this one, if you let u equals x squared, that's going to be good because it's going to, you're looking for something that accomplishes two things. One, its derivative will give you the correct power of x on top, and then when you square it, it will give you then the power of x you want here. And it kind of has to work that way anyway to make these fit. I'm not interested in asking integral problems on an exam that don't work. Not everything can be integrated, but I'm not interested in asking things that can't. So, well, anyway, I didn't put that u squared equals x to the fourth, but it would. And then a would be 3. But you see, you have a 1/2 du equals x dx. So that takes care of your numerator. There's the 1/2 and the du. Now we have this 1/2 right here. So now it's set up du over 9 minus u squared, which fits that formula perfectly. And then you have a 1 over 2a. So this 1 over 2 is from the formula. A is 3. So we have 3 terms down here. So 2 times 2 times 3 is 1/12. And we have a plus u over a minus u. So we'd have 3 plus x squared over 3 minus x squared. And there we go. You got to be real careful, when you look at these, because there's kind of, look at these integrals. They're kind of similar here. And always remember that if your integral form is plus, that, the order doesn't matter that they're written in. Only subtraction does. So notice this one, like with these pluses and minus, that means if it's plus, this will be plus. If this plus or minus, it'll be minus. Now, I've seen some formulas where these are reversed. We'll say plus and minus here, and then minus plus there. That means it would be the opposite. If it's plus over here, it's minus there, minus plus. But these are the same because they're written the same way. But anyway, point being is that for this top formula, for example, if under the radical you had a squared plus u squared, that's exactly the same thing. But it's minus that makes the difference. U squared minus a squared is this formula. A squared minus u squared is arc sine. So this was one formula we used right here for that problem. So be very careful. Now the next one I just kind of threw in there that I just kind of reviewed a basic integral problem. So where that's just, it just goes back to earlier. So that just ends up being natural log because it doesn't have to be set up like this. So you let u be the entire denominator, du fits on top, and it's pretty straightforward natural log from there. So now let's come back to our new business here. Let's take a look at this one. This looks like fun. Now, kind of sneaky with those odd exponents. We've seen that back earlier with the inverse trig integration, because instinctively you think that u squared might have to be a positive an integer, even integer exponent like 2 or 4 or 6. But you can actually square a variable to get to an odd exponent. It just means that variable is going to have a 2 in the denominator. That way when you square it, they'll get rid of the 2. So I'm looking at this going, well, I kind of jumped ahead here, but I figured that u2 had to be x cubed, and then let u equal x to the 3/2, and that's actually what works out beautifully, because we have the u squared, and because x to the 3/2 then has the derivative of an x to the 1/2. So we bring the 3/2 down, x to the 1/2, and there's our square root of x on top. So it fits beautifully. So we have 3/2, so it's 2/3 when we flip it over. So that means our numerator here, square root of x dx, is 2/3 du. And then we have square root of 4 plus u squared. So I would have looked at those formula rules, and I would have come to this conclusion right here. Fits that formula. And just like I was saying a minute ago, because the order, it doesn't matter. X cubed, since it's plus. X cubed plus 4, 4 plus x cubed, look at that, perfect. It fits this one. And so we didn't have the 2/3 comes from the adjustment, of course. You have ln of u, which is x to the 3/2, plus the square root of u squared plus a squared. Okay, obviously that makes no difference, but instead of 4 plus x cubed, I have x cubed plus 4. And then, of course, with any definite integral, we have our plus c. All right, very good. These aren't too bad. Here's a little completing the square action here. So I'm looking at this. I can tell something's going to have to be done to that quadratic. Now here's a really good clue on this one. You can kind of identify that that's going to be a u, which probably means you're going to have x plus 2 squared under the radical to be u squared. And sure enough, if I do the plus 4 here to complete the square minus 4, I get x plus 2 squared plus 4. So I was definitely expecting the x plus 2 squared. So u is x plus 2, du is dx, a squared is 4, which makes a equal 2. And then, so there's the general sort of shell for the formula there for ours. Du over u squared plus 4. I could have put 4 plus u squared, because once again, plus doesn't matter, but it clearly fits this one. Got to be very careful, because it looks a little like, scroll back up here, you might be tricked into thinking it's arc seek, but no, because of the minus for arc seek. Ours is plus. So that's actually an inverse hyperbolic function. I guess I could scroll up here real quick, and we can see which one it is, sort of. Looks like it's probably this cosec inverse here, if it's that, maybe. Anyway, it doesn't matter. Unless someone requires you to matter, it doesn't matter to me. But so here's the formula. So a is 2. We had no adjustments for du, so nothing else comes out here. So it's negative 1 over 2, negative 1/2, natural log, and there we go, a plus. I left it like this under the radical. Obviously, x squared plus 4x plus 8 would have been accurate right there. And then over the absolute value of x plus 2, then plus c. So let's kind of take a look at this one. U kind of needs to be 2x, and that works out well, because this one won't have to complete the square here. But u squared then will be 4x squared, because we square the 2, remember? So du will be 2 dx, so 1/2 du equals dx, so there's the 1/2. And now it fits this one right here, which fits this form right here. I'm not a big fan of having 1 right there under the radical. You can see from this other example, I had redone this problem. Yeah, I kind of changed that 1 to a 4. I mean, it's not that I hate the number 1 per se or anything like that. It's just, if it's 1, that's a squared. A is also 1. You don't even have to take this. You could forget to take the square root and you'd still be right. So, I want you at least, like if it, so yeah, I'd rather that be like a 4 or 9 or something, so you would know that a would equal the square root of that. But since the square root of 1 is 1, kind of makes it a no-brainer. Plus it's kind of boring right here too. So I like a to be something other than 1. So I got a 1/2 adjustment right here. It comes out. Formula says negative 1 over a, so it's negative 1 over 1. I didn't even bother to rewrite this. Obviously, that's just going to be negative 1/2. But I wanted to write it like this first so you can see clearly where it came from. If I just wrote negative 1/2, it might be a little unclear. And then we have, all right, fits the formula right here. 1 plus the square root of 1 minus 4x squared, and then over the absolute value of 2x. And that concludes the video for hyperbolic functions.